Between galaxies, where matter thins into near-perfect emptiness, the universe is not resting. It is stretching quietly, relentlessly, as if the dark spaces themselves have learned a new intention. It does not blaze like a star. It does not detonate like a supernova. It does not whirl like a storm of gravity. It simply persists, an invisible pressure written into the vacuum, patient enough to outlast every shining thing. Across billions of light years, distant galaxies drift apart faster than gravity alone should allow. Their ancient light arriving with a message that feels almost impossible. The expansion is accelerating. The first clear warning came at the end of the 20th century, when astronomers used exploding stars type Ia supernovas, cosmic mile markers. The measurements did not reveal a slowing universe, but a speeding one. Later, the faint afterglow of the Big Bang in the cosmic microwave background, and the large-scale patterns of galaxies reinforce the same unsettling truth. Something dominates the cosmic budget, yet refuses to be seen. Science gave it a gentle name, dark energy, a placeholder for the hidden side of the cosmos, the part that does not glow, does not clump, and yet shapes the fate of time. Einstein once wrote a term into his equations to steady the universe, then regretted it. Decades later, that abandoned idea returned like an echo with teeth. If this force is constant, the far future becomes a slow fading into cold isolation. If it evolves, the laws of physics may be temporary treaties, breakable, revisable, fragile. In the most unsettling possibility, even the vacuum may be metastable, and reality itself may be balanced on a deeper, unseen edge. One mystery remains, pressing against everything. What is driving the acceleration of the universe, and what ends when the cosmos reaches the end of its hidden side? Asterisk, the sentence arrives without drama, in the language of papers and plots, yet it carries the weight of a myth. The expansion is speeding up. Not merely continuing, not slowly coasting on ancient momentum, but accelerating, gaining distance faster with each passing epoch, as if the universe has discovered a hidden slope beneath its own feet. For centuries, gravity had been the expected narrator of cosmic fate. Mass gathers, curved space-time, pulls inward. In every familiar story written on Earth, attraction is the rule and slowing is the consequence. A thrown stone rises, hesitates, then returns. A planet circles, held by a central pull. Even in the grandest cosmological imagination, expansion was supposed to be a firework, violent at first, then gradually tamed by the collective gravity of everything that exists. Acceleration reverses that intuition. It asks physics to accept that on the largest scales. The universe behaves as though it contains a form of energy that resists gravity's usual command. Not by pushing, in the ordinary sense, like wind against a sail, but by altering the geometry of space-time so that separation itself becomes easier, and then easier still as space grows. General relativity allows such behavior, but only through a mechanism that feels almost like a loophole. In Einstein's equations, gravity is not sourced only by mass. It is sourced by energy density and pressure together. Pressures so humble in human experience. So tied to air in a room or water in a pipe becomes a cosmic actor in spacetime's curvature. Under the right conditions, pressure can contribute to attraction. Under stranger conditions, pressure can flip the sign of fate. The mathematics condenses this into a single, unsettling requirement. In an expanding universe, described by the Friedmann equations, acceleration occurs when the cosmic fluid has sufficiently negative pressure. Commonly expressed through an equation of state parameter, W equals P rho. Ordinary matter has negligible pressure compared to its energy density, and radiation has positive pressure. Both slow expansion. But if a component exists with W1/3, then the expansion accelerates. A cosmological constant corresponds to W equals 1, the most serene and relentless form of cosmic acceleration, an energy density that does not thin out as space grows, and a negative pressure that remains constant as time passes. It is here that the shock becomes more than a surprise. It becomes a rupture in the idea of empty. Because the simplest way to produce acceleration is to give vacuum itself an energy and intrinsic density belonging not to matter, not to light, not to any drifting particle, but to the fabric of spacetime. The emptiest regions between galaxies would not be truly empty. They would be filled with something that cannot be photographed, cannot be bottled, and cannot be shielded. It shapes the evolution of everything. Scientists named the unknown driver dark energy. But the phrase is not an explanation. It is a boundary marker around ignorance. It says, there is an effect, there is a measurable influence, and it behaves like an energy with negative pressure. Beyond that, the darkness returns. The psychological violence of the discovery lies in how it inverts the expected hierarchy of reality. In the old intuition, the universe was made mostly of luminous things, stars, galaxies, the structures that can be seen. Then came the first dethroning. Most matter is dark, unseen, inferred by its gravity. Dark matter, whatever it is, clumps and scaffolds galaxies, shaping the cosmic web. Yet dark matter behaves at least like matter. It attracts, it gathers, it builds. Dark energy does the opposite. It does not clump. It does not form halos. It does not make galaxies. It appears almost perfectly smooth, spread across space like a silent background note. And the more space exists, the more influential it becomes. Not because it grows denser, but because it occupies more volume. In a universe where matter dilutes as expansion proceeds, a constant vacuum energy does not dilute at all. Over time, the hidden component inevitably takes control, not by becoming stronger in itself, but by outlasting everything that fades. It is an idea that feels, in human terms, like a victory of absence over presence. This is why the discovery reads like a betrayal of common sense. The cosmos appears to be governed by something that looks like the energy of nothing, an invisible pressure that dominates the cosmic budget. The universe becomes a story in which emptiness has the final say. Then comes the deeper insult. The equations that permit this behavior are old, but the implications collide with the most cherished frameworks of modern physics. For if dark energy is vacuum energy, if it is the cosmological constant, lambda, then the value of that constant is not merely small. It is impossibly small compared to what quantum theory seems to predict. Quantum field theory. The framework that describes matter and forces as fields permeating spacetime cannot keep vacuum truly silent. Even in the lowest energy state, fields possess zero-point fluctuations. In a simplistic picture, each mode of each field contributes a small amount of energy. And when those contributions are summed across all possible modes, the result diverges. In practice, physicists impose a cutoff and renormalize. And the theory continues to make extraordinarily accurate predictions in laboratories. But when that vacuum energy is treated as something that should gravitate when it is inserted into general relativity as a contribution to the cosmological constant, the naive expectation becomes enormous. Depending on the cutoff scale and the details of the calculation, the predicted vacuum energy density can exceed the observed value by an absurd factor. Often cited as roughly 10 in dimensionless terms, it is not a discrepancy of a few percent. It is a chasm so wide that it feels like a message. Either the calculation is being interpreted in a fundamentally wrong way, or some unknown mechanism cancels the vacuum energy almost perfectly, leaving a tiny residue, the exact residue the universe uses to accelerate. This is the cosmological constant problem, and it is not a minor technicality. It is a collision between two pillars of 20th century physics. General relativity, the geometry of gravity, is exquisitely confirmed on many scales. From the bending of light to the orbits of planets, quantum field theory is the engine of particle physics, confirmed in accelerators and experiments with staggering precision. Yet when the vacuum is asked to play in both arenas at once, the numbers become surreal. The problem has the flavor of a paradox that should not be survivable. If vacuum energy is as large as naive quantum estimates suggest, the universe would have expanded too violently for galaxies to form. Structure would have been torn apart before it could begin. There would be no cosmic web, no stars, no long-lived chemistry. the sky would not be filled with galaxies. It would be an empty scream. Instead, the sky is full. The cosmos is gentle enough to allow complexity, but it accelerates just enough to be measurable, just enough to be decisive, small enough to be incomprehensible. This is not merely an open question. It is a wound in the theoretical unity of physics. The second paradox is quieter, but it cuts with a different kind of precision. Even if the cosmological constant is accepted as a given, just a number that nature chose, the timing still feels uncanny. Matter density decreases as the universe expands. Radiation decreases even faster. A cosmological constant stays constant. That means that at early times, matter and radiation dominated. At late times, vacuum energy dominates. There is, inevitably, a transition era where the densities become comparable, an era where the hidden side and the visible structures are balanced closely enough for the acceleration to reveal itself. The unsettling part is not that such an era exists. The unsettling part is that it appears to be now in the vast lifespan of the universe. With its billions of years behind and possibly unbounded time ahead, why should observers happen to live near the moment when dark energy begins to dominate? Why does the cosmic ledger place humanity and its telescopes in a thin slice of time, where the two components are of the same order? Why is the hidden side revealing its hand in this epoch, rather than in a distant future when no stars remain to witness it, or in a deep past when observers could not exist? This is the coincidence problem. It is not a proof of anything. It is a discomfort that refuses to go away. It suggests that either the timing is a consequence of selection observers arise in eras that permit structure and complexity, or that the explanation for dark energy is not a constant at all, but a dynamical phenomenon whose behavior tracks cosmic evolution in a more natural way. And that is where the story begins to feel like it is being narrated by the cosmos itself. With a deliberate cadence, first the shock of acceleration, then the insult of the vacuum energy discrepancy, then the eerie coincidence of timing, each step pushing science toward the possibility that something fundamental is missing. The emotional stakes of this mystery are not limited to equations. Acceleration changes not only the future of matter, but the future of knowledge. As the universe accelerates, horizons form not walls of material, but boundaries of causality and visibility. In an accelerating spacetime, distant galaxies can slip beyond a cosmic event horizon. Their light, emitted today, may never reach the future. Over time, more regions of the cosmos become unreachable, not because technology is weak, but because the geometry of spacetime itself stretches faster than signals can cross. The universe becomes an archipelago of islands, each isolated by expanding darkness. From the perspective of a future civilization bound to a galaxy group, the sky would change. Nearby galaxies would remain gravitationally bound, at least those close enough to resist the accelerating expansion. But the more distant galaxies would redshift, dim, and eventually fade from detectability. Their photons would be stretched into wavelengths so long that they would dissolve into background noise. The relic radiation of the Big Bang, already faint, would slide further into obscurity, its wavelength elongated until it becomes almost impossible to measure in such a future. The evidence for cosmic expansion itself could disappear. The universe would look from within a single gravitationally bound region, like a static island surrounded by emptiness. The great story of the Big Bang and cosmic evolution could become inaccessible, not because it is untrue, but because the observable record has been stretched beyond retrieval. Acceleration is thus a kind of cosmic erasure. Not an explosion that destroys, but a slow process that removes information from the horizon. It edits the universe's autobiography. This is why dark energy feels philosophical. It does not merely threaten physical structures, it threatens the human relationship to the cosmos as a knowable thing. The more the universe accelerates, the smaller the portion of it that can ever be studied. And the more the deep past becomes a fading whisper, the physics behind this erasure can be expressed with precision. But the result has a poetic cruelty. In a universe dominated by a cosmological constant, space-time approaches a de Sitter-like state, exponential expansion, a horizon, a persistent separation. Even emptiness gains a kind of temperature associated with the horizon and abstract. Remnant of thermodynamics in a place that feels too cold for concepts like heat, the cosmos becomes smooth, vast, and quiet. If it is choosing stillness over structure, yet the most unsettling aspect is that the story may not be fixed. The cosmological constant is the simplest explanation, but it is not the only one. If dark energy is not constantive, it is a dynamical field. Often imagined as a scalar field slowly evolving, then the acceleration could change with time. Its equation of state parameter could drift. Its energy density could rise or fall. It could mimic a constant today while behaving differently in the far future. In such scenarios, the end of the cosmos is no longer a simple fade. It becomes a question mark. If the hidden energy weakens, acceleration might slow. If it strengthens, it could lead to catastrophic futures, such as the Big Rip, where expansion ultimately overwhelms all binding forces. If it behaves in more complex ways, it could trigger transitions in the vacuum itself, phase changes in the fields that define reality. Even the possibility remains that acceleration is not driven by an energy component at all, but by a breakdown of general relativity on the largest scales. Requiring a modified theory of gravity, each possibility leaves fingerprints in data, in how galaxies cluster, in how lensing grows, and how supernova map the expansion history. Each possibility demands patience, because the cosmos reveals itself not in laboratory timescales, but in surveys and statistics spanning decades, but the shock remains the same. Regardless of which theoretical door is opened, the universe is forcing a statement that feels like a contradiction of gravity's character. Expansion is speeding up. Space, once imagined as a passive stage, is behaving like an active actor one with an unseen motive. The hidden side of the cosmos is not merely a missing piece. It is a missing rule. It sits at the intersection of quantum theory and gravity, of observation and horizon, of time's arrow and the fate of structure. It raises the possibility that the laws of physics, so carefully assembled from terrestrial experiments and stellar observations, may be incomplete in the only arena large enough to test their deepest assumptions. And so the central suspense sharpens into a single, persistent question, simple enough to be spoken in one breath, and profound enough to resist a century of thought. Is dark energy a constant property of empty space, an unchanging term woven into reality's equations, or is it evolving with time, quietly rewriting the universe's future, while the last era capable of understanding it struggles to measure the change? The deeper the night became, the more carefully it had to be measured. Once the first shock of acceleration settled into the scientific record, the mystery changed shape. It was no longer enough to say that the universe was speeding up. The hidden side had to be tested from multiple angles, as if reality could only be cornered by surrounding it with different kinds of evidence, different eyes, each sensitive to a different weakness in the darkness. In modern cosmology, certainty is rarely granted by a single instrument. It is negotiated through convergence, independent methods, separate systematics, different data pipelines, all arriving at the same quiet conclusion. The supernova remained the first voice in the story. Mall. Temporary stars used as mile markers across deep time. Type Ia supernova are not chosen because they are perfect, but because they are consistent enough to be standardized. Their peak brightness correlates with the shape of their light curve, allowing astronomers to convert an observed explosion into a distance estimate. Yet the deeper the surveys reached, the more the universe demanded humility. Dust can dim light. Host galaxies can bias the sample. Selection effects can favor brighter events at higher redshift. Even the act of discovery can create a subtle distortion. A telescope cannot record what it cannot detect. So supernova cosmology became a discipline of calibration and restraint. Larger compilations emerged, built not just to increase numbers, but to domesticate error. Thousands of light curves spanning nearby galaxies to deep redshift were assembled with improved treatment of systematic uncertainties. The Pantheon Plus analysis, for example, expanded the sample and strengthened the statistical power while explicitly grappling with the ways. Observational bias can masquerade as cosmology. Arxiv, the more carefully those biases were modeled. The more the supernova continued to whisper the same implication. A universe whose expansion history cannot be explained by matter and radiation alone. But the hidden side of the cosmos is too large to be trusted to a single candle. A second witness was needed, something ancient, something physical, something imprinted into the distribution of galaxies themselves. This is where the story turns to a relic pattern from the early universe: baryon acoustic oscillations. Long before stars ignited, the cosmos was a hot plasma of photons and matter locked together in a tight dance. Pressure waves moved through that primordial soup sound in a universe without air. When the cosmos cooled enough for atoms to form and light to decouple, those waves froze into a preferred scale, a faint statistical ripple in how matter clustered billions of years later. That ripple still exists as a standard ruler. Visible in the spacing of galaxies across immense volumes, it is not seen in a single structure, but in the collective pattern, as if the universe kept an ancient metronome hidden inside the cosmic web. Measure that scale at different redshifts, and it becomes possible to trace how distances and expansion changed over time, independent of supernova brightness. This is where the investigation becomes cinematic. In its method, one technique listens for explosions, another listens for fossil waves. Both point toward the same unseen driver. And then comes the earliest portrait of all the cosmic microwave background. The CMB is not merely a glow. It is a time capsule, a map of the universe when it was only about 380,000 years old. Its tiny temperature fluctuations encode the initial conditions from which galaxies later grew. When combined with other probes, CMB measurements anchor the geometry of the cosmos and constrain the overall energy budget. The Planck results, in particular, helped solidify the standard cosmological framework and showed that a dark energy component consistent with a cosmological constant remains compatible with multiple datasets. A and a +1 in narrative terms, the CMB is the opening scene of the universe, recorded in microwaves instead of light. Supernova and galaxy clustering are later chapters. The investigation gains power because it reads the same story at different ages. If the plot is consistent, the mystery becomes harder to dismiss as error. Yet the hidden side of the cosmos does not reveal itself only through distance. It also reveals itself through resistance, through the way it competes with gravities. Attempt to build structure. This is the third eye. Weak gravitational lensing and the growth of the cosmic web. Gravity bends light. Not dramatically, as in the famous arcs around galaxy clusters, but subtly, everywhere. Each galaxy image is a tiny smear caused by the matter between it and the observer, dark matter halos, fluments, sheets, the invisible scaffolding holding the luminous universe in place. Weak lensing is not a single spectacular event. It is a statistical effect measured across millions of galaxies, each one slightly distorted. The pattern of those distortions maps how matter is distributed, and how that distribution evolved with time. This matters because dark energy and cosmic acceleration change the rate at which structures grow. In a universe without acceleration, matter has more time and more gravitational dominance to clump into denser webs. In an accelerating universe, expansion becomes an adversary. It stretches space, reduces the effective pull between distant regions, and can slow the growth of large-scale structure. So cosmology becomes a two-front campaign. One front measures expansion history, the geometry of how distances change. The other measures structure growth, the dynamic story of how matter responds. If both fronts agree, a simple model survives. If they diverge, the hidden side is no longer a single unknown number. It becomes a clue to deeper physics. Surveys such as the dark energy survey turned weak lensing and galaxy clustering into a precision instrument, explicitly combining multiple measurements to constrain cosmological parameters and test extensions beyond the simplest model. Dark energy survey +1, the details can be technical nuisance parameters, intrinsic alignments, photometric redshift uncertainties, but the narrative meaning is clear. The universe is being examined not only by how far objects are, but by how the invisible mass between them has assembled, and still in this growing forest of evidence. The simplest description often remains stubbornly adequate, a cosmological constant. Lambda, paired with cold, dark matter CDM. It is elegant. It is minimal. It fits a wide range of data, yet the deeper investigation is not only about confirmation. It is about catching the hidden side in motion. If motion exists at all, that is why the next phase of the story becomes defined by scale, by mapping not thousands or millions, but tens of millions of cosmic objects to reveal a pattern too faint to see otherwise. The Dark Energy Spectroscopic Instrument, DESI, was designed for precisely this kind of interrogation. A massive redshift survey capable of creating the largest three-dimensional map of the universe ever constructed, tracing how matter has arranged itself across billions of years, and reading Bo as a ruler across time. In March 2025, DESI collaboration results reported strengthened hints that dark energy may be evolving rather than remaining a perfectly constant. A cosmological term and unsettling suggestion, presented carefully, because hints are not verdicts. Barclay Lab News +1, this is a delicate moment in the narrative of science, because modern cosmology lives in the realm where precision can make the unknown feel close enough to touch and not close enough to claim. DESI's method is not mystical. It is brutal in its scale and patience. Spectroscopy measures redshift, the stretching of light's wavelength due to cosmic expansion. With enough redshifts, it becomes possible to build a three-dimensional map and detect statistical patterns like Bo with increasing precision. But what makes DESI pivotal is not only its size, it is its timeline. It traces the expansion history across a large fraction of cosmic age over, roughly the past 11 billion years, testing whether the acceleration behaves like a constant background pressure, or like something that has changed its character over time. Berkeley Lab News: if dark energy is a cosmological constant, it should be consistent across epochs. The equation of state parameter W should remain close to -1. If it is a dynamic field quintessence-like behavior, then W might drift. Or the inferred expansion history might show subtle deviations from CDM expectations when combined with other probes. The phrase hints that dark energy may evolve, carries a particular kind of tension. It implies that the hidden side might not be a fixed feature of empty space, but a living term in the cosmic story, changing slowly, perhaps too slowly for any one generation to fully resolve, but changing enough that statistical trends begin to accumulate. And still, even the most careful hints require caution, because the universe is not only mysterious, it is also merciless in how it hides systematic errors. Different datasets carry different vulnerabilities. Supernovae require calibration and careful treatment of local effects and selection biases. Galaxy clustering relies on understanding survey completeness and the relationship between luminous tracers and underlying matter. Weak lensing depends on shape, measurement accuracy, redshift estimation, and the subtle astrophysical alignments of galaxies. CMB constraints are exquisitely precise, but anchored to early universe physics and assumptions about the model, connecting early and late times so the deeper investigation becomes a choreography of cross-checks. Data is combined not because combination is fashionable, but because combination is an interrogation technique. If a deviation appears only when one dataset dominates, it might be a systematic echo. If it persists across independent probes, it begins to look like physics. This is how the hidden side is pursued, through consistency tests, through internal tension analyses, through model comparisons and parameterizations that search for evolution without forcing it. There is a reason cosmologists describe the universe in terms like constraints. The cosmos is not speaking directly. It is being cornered statistically. Each new dataset does not merely reduce error bars. It changes the geometry of uncertainty, turning wide possibilities into narrow corridors. And yet, in those narrowing corridors, the mystery becomes sharper rather than smaller. Because even if the simplest model continues to fit, The act of fitting exposes the fragility of the assumptions underneath. CDM works remarkably well. But it is also a model built from components that are not directly detected in their fundamental form. Dark matter is inferred. Dark energy is inferred. The standard model of cosmology is a triumph of predictive structure, yet it is also a map with blank countenance. It's labeled in pencil. Desi's hints of evolution, reported with restraint, arrive into that philosophical context like a tremor beneath a city that has stood for centuries. Barclay Lab News +1, even if the tremor turns out to be noise. It reveals how sensitive the foundations have become, and the tremor has already sparked responses in the scientific ecosystem arcs of discussions, robustness tests, alternative parameterizations, scrutiny of low redshift supernova calibration, and debates about how model choice can shape inference. ArcSiv +1, the hidden side, is not only a cosmic force, it is now an active battlefield of methodology, where the line between discovery and bias can be as thin as a correction term. This is the nature of deeper investigation. The closer science gets to the edge of its ignorance, the more the instruments begin to measure not only the universe, but the limits of the tools used to measure it. So the chapter's tension resolves into a quiet but powerful state. The evidence for acceleration is not resting on one observation anymore. It has become a woven fabric. Supernova distance ladders tightened by larger samples and systematic modeling. BAO rulers traced through galaxy maps, CMB portraits anchoring geometry, weak lensing patterns revealing structure growth. Barclay Lab News +3, ArcSiv +3a, and a +3, the hidden side does not fade under scrutiny. It becomes more sharply defined, more mathematically constrained, more inescapable. And yet it remains ungraspable, in essence. Because the deeper the universe is measured, the more the question transforms. The mystery is no longer merely does dark energy exist. The mystery becomes, is the hidden side static, like a constant written into the vacuum? Or is it dynamic, like a field with its own evolution? In the first case, the cosmos is ruled by a number small, strange, inexplicably tuned, but fixed. In the second case, the cosmos is ruled by a process something that might have a history and therefore a future different from what the simplest model predicts. The investigation has not yet delivered a final verdict, but it has done something almost as consequential. It has made the mystery testable, and it has begun to reveal hairline cracks, subtle tensions, and trends like stress patterns in a mirror that still appears intact, yet might not remain so forever. In that mirror, the universe continues to accelerate, quietly enlarging the darkness between galaxies, while instruments built from glass and silicon attempt to catch the hidden side in the act of changing its mind. The deeper the universe is measured, the more the mystery stops behaving like a missing number and begins to feel like a moving presence. Acceleration was once a single, surprising curve on a plot, an unexpected bend in the expansion history. But precision turns curves into verdicts, and verdicts into unease. Each new generation of data narrows the allowed space for explanations. It's not by revealing the hidden side directly, but by tightening the boundaries around how it must behave. In that tightening, a quiet suspicion grows. The force called dark energy may not be a fixed background hum. It may be changing slowly, imperceptibly, on human timescales, but decisively across cosmic time. Cosmology has a language for that suspicion. It speaks in a single ratio, an equation of state parameter, W, relating pressure to energy density. In the simplest picture, Einstein's cosmological constant W sits at -1. It's perfectly steady, as if the vacuum carries a constant, timeless pressure embedded in space-time itself. The acceleration becomes an inevitability as matter thins with expansion. The vacuum remains, and the vacuum eventually dominates. But the deeper investigation has forced the possibility that W might not remain exactly -1. It might drift. It might evolve. Parameterized dark energy is not introduced as a flourish of theory, but as a controlled way to ask whether the universe is hiding a change in its own rules. A common approach allows W to vary with time. It's often expressed through a two-parameter form that can mimic a constant today while tilting in the past or the future. In that mathematical allowance, the mystery gains a darker edge. If the cosmic push evolves, then the cosmos is not merely coasting toward darkness. It is selecting a trajectory, as if expansion has become a living term in the story rather than a static condition. This is where the tone of the universe turns quietly horrific, not with monsters, but with consequences. If dark energy is constant, the far future is not a sudden catastrophe. It is a slow thinning, a long exile of galaxies from one another. NASA's own descriptions of cosmic history note that, after an early era when gravity slowed expansion, the universe's expansion began speeding up again billions of years later under the influence of what is now called dark energy. NASA science, if that influence remains constant, the cosmos approaches a state in which distances grow ever faster and horizons become more decisive. Over immense spans of time, galaxies beyond a certain distance slip away so completely that their light, emitted in the far future, can never arrive. The observable universe becomes a shrinking island of information surrounded by expanding absence. The night sky in such a future would not be filled with revelations. It would be filled with loss. The cosmic microwave background, already faint, would be stretched into wavelengths so long and energies so low that it becomes nearly impossible to detect. Evidence of a beginning would fade from reach. Not because the beginning did not happen, but because the record has been pulled beyond the horizon of measurement. Expansion becomes a form of erasure, a patient editor removing pages from the cosmic archive. Stars continue for a time. Galaxies still orbit within their bound groups. But the overall direction is isolation. The universe grows older, emptier, more silent. The phrase heat death is not poetry. Yet it describes a poetic emptiness, a future of maximum entropy where usable energy becomes scarce. Structures decay, and time continues without the drama of new complexity. In that scenario, the hidden side's victory is not an explosion. It is a quiet dilution of meaning, a fading into a cosmos so spread out that nothing can easily happen again. And even this gentle ending carries a philosophical wound. A constant cosmological constant is, on paper, the simplest explanation. Yet its simplicity hides the most unsettling implication. The universe may be ruled by a property of nothingness that never changes, an invisible constant that outlasts every atom and every star. But the deeper the measurements become, the more science is forced to stare at another possibility. The dark energy is not constant and not gentle. If dark energy grows stronger over time, if its equation of state slips below -1 into phantom territory, then the acceleration is not merely exponential drift. It becomes a countdown. In such models, the energy density of dark energy increases as the universe expands, leading to a divergence in a finite time, a cosmic doomsday not driven by collapse, but by runaway expansion. This is not a speculative invention of science fiction. It is a real theoretical scenario explored in the literature, where W-1 produces a future in which the scale factor becomes infinite in a finite interval. Arcsiv +1, the horror of phantom energy, is not that it arrives loudly. It arrives mathematically with a calm inevitability that feels more frightening than violence. As dark energy grows, it does not simply separate galaxies. It begins to overcome every binding force in stages. First, the largest structures lose coherence. Galaxy clusters held together by gravity across millions of light-years are the earliest to weaken. The expansion does not tear them apart like a hand ripping paper. It gradually makes their gravitational bonds insufficient against an accelerating background that grows stronger each day. Then galaxies themselves become unstable, their stars no longer securely bound in the long run. In the later approach to the rip, the scale of destruction shrinks from cosmic to intimate. Solar systems become unable to maintain orbits. Planets lose their paths and drift away. Eventually, the expansion becomes strong enough that even the forces within matter begin to fail. Molecules, atoms, and the very fields that define stable particles can be torn apart by the accelerating geometry of space-time. The end is not a singular explosion. It is a progressive, unbinding structure failing from the outside inward until nothing remains to hold shape. This sequence was formalized as the Big Rip, and it has been discussed in both technical and popular scientific writing as a possible cosmic endpoint if phantom energy were real. Arxiv +1, the scenario is extreme, and current data does not demand it. Yet its presence in the list of credible outcomes is part of what makes the hidden side so unsettling. The same mystery that could yield a cold fade could also yield a catastrophic unmaking. The deeper investigation does not merely ask which ending is true, it asks whether the universe is stable enough to have endings at all. Because beneath the question of W lies another possibility, colder and stranger, that the vacuum itself may not be the true ground state of reality, that the universe might be living in a long-lived metastable pause. In quantum field theory, a vacuum is not simply empty space. It is the lowest energy state of a set of fields. Yet in many field theories, multiple vacuum states can exist, local minima, separated by barriers. A false vacuum is a state that is stable in the short term, trapped behind an energy barrier but not absolutely stable. Quantum mechanics allows tunneling. A system can, in principle, transition from the false vacuum to a lower energy true vacuum through a process called vacuum decay. This idea is not a vague metaphor. It has a formal semi-classical description. Sidney Coleman's work on the fate of the false vacuum developed the framework for understanding how such transitions can occur through bounce solutions, rare nucleation, events that create a bubble of the lower energy phase. LMU Munich Physics +1 Coleman and DeLucia then extended this to include gravity, showing that spacetime curvature can alter the decay process in profound ways. APS Physics +1, if such a decay occurred in the vacuum of the universe, the consequences would depend on the difference between vacuum states and on how fundamental constants and forces change inside the new phase. The unsettling part is not merely the destruction of structures. It is the possibility of a rewriting. Particle masses, force strengths, even the stability of atoms could change. The familiar universe would not simply be torn apart. It would be replaced by a different set of physical rules, spreading outward at essentially the speed of light in most discussions. The probability of such decay in the current universe is extraordinarily low, so low that the cosmos appears stable on timescales far longer than its current age. Analyses of electroweak vacuum stability in the Standard Model, including work that considered the implications of Higgs's mass values, have explored the possibility that the universe may be metastable, yet long-lived. CERN Document Server +1, a metastable vacuum that lasts vastly longer than the age of the universe, is not a contradiction. It is a reminder that cosmic safety can be statistical rather than absolute. This is where the hidden side of the cosmos begins to resemble a philosophical horror. Dark energy is not only a force that shapes expansion, it is also a clue about the vacuum, about whether empty space is truly stable, whether the ground state is settled, whether reality is resting in its deepest minimum or merely paused above it. And here, the threads converge into a single tightening knot. If dark energy is a cosmological constant, it may be vacuum energy, an intrinsic property of space. If it is a dynamic field, it may be a scalar rolling slowly through a potential landscape, changing its pressure-to-density ratio over time. If it is linked to a deeper vacuum structure, then cosmic acceleration may be a symptom of a universe it's not fully relaxed into its final state. Each of these interpretations changes the meaning of the same observations. The same supernova, the same fossil acoustic rulers, same background radiation become the language of different endings. This is why tensions matter so much. A tension is not a failure. It is a hint that the hidden side may not fit into a single constant. When measurements tighten and small discrepancies persist across different probes, science is forced to consider whether the simplest model is being held together by coincidence rather than truth. The dark energy spectroscopic instrument has been presented as one of the most powerful current attempts to catch that subtle drift in behavior mapping the expansion. History across much of cosmic time and reporting strengthened hints that dark energy may be evolving rather than remaining perfectly constant. DESI +2 Symmetry Magazine +2 Journalistic. Summaries of those results have described the possibility that dark energy may be weakening over time. Based on DESI's multi-year mapping of tens of millions of galaxies and quasars combined with other cosmological datasets, Reuters plus one such hints do not crown a new theory. They do something more subtle. They shift the emotional posture of the mystery. A constant cosmological constant begins to feel less like a conclusion and more like a temporary truce. An agreement that holds until the data becomes sharp enough to break it. In the language of cosmology, every candidate for dark energy must answer to questions. The first is geometric. Does it reproduce the observed expansion history? The second is dynamical. Does it predict the observed growth of structure? A constant vacuum energy produces a particular relationship between these two, an elegant consistency inside general relativity. Dynamic fields and modified gravity can produce different relationships, sometimes leaving fingerprints that precision surveys can detect. So the escalation is not merely about scarier endings. It is about the possibility that the hidden side is active. It participates in the unfolding rather than sitting as a static backdrop. The most unsettling thought is not that the universe ends cold or violently. It is that the universe may be changing its rules, while observers are still capable of noticing in that light. The acceleration becomes more than a measured phenomenon. It becomes a kind of cosmic agency, not in the sense of intention, but in the sense of evolution. The cosmos may not be a fixed machine running down. It may be a dynamic system moving through phases. If the next decades confirm that W is exactly -1 and never deviates, the hidden side remains mysterious, but stable and inexplicable constant governing the largest scales. If W drifts even slightly, then the hidden side becomes a field with history, and the far future becomes open. If the vacuum stability is questioned, then every ending becomes a subset of a deeper question. Whether the current universe is the final version of reality or merely a long-lived chapter in a larger landscape of possible laws, that is the slow reveal at the heart of this chapter. The deeper the measurements go, the more the unknown stops, looking like a missing puzzle piece, and begins to look like a hinge, something upon which the entire future swings. Acceleration is already changing the cosmos, separating galaxies and carving horizons into space-time. What remains unresolved is whether acceleration is the calm work of a constant vacuum, or the first sign that the hidden side is not finished changing. The final tension sharpens into a single, persistent uncertainty. The hidden pressure behind expansion may be constant. It may be evolving. Or it may be pointing toward a vacuum structure deeper than the current laws can fully describe. In each case, the universe is not only expanding, it is revealing slowly that emptiness may have layers and that the future may depend on which layer is real. Theories and speculations, when a mystery refuses to show its face, science learns to study its shadow. Dark energy, this hidden pressure driving cosmic acceleration, does not appear in telescopes as a glowing object, does not leave tracks in detectors as a passing particle, does not gather into halos or form luminous structures. It is inferred from geometry, from the way distances change, and the way the cosmic web grows less eagerly than gravity alone would suggest. And so the search for its nature becomes a procession of doors, each one a plausible passage into the unknown, each one shaped by the same measured fact. Space is stretching faster than expected. The first door is also the quietest, and perhaps the most unsettling in its simplicity, the cosmological constant lambda. In Einstein's general relativity, the universe is not a stage where matter performs. It is a fabric whose curvature is the performance. Energy and momentum shape space-time, and space-time shapes motion. Yet Einstein's equations allow an additional term, an intrinsic property of space-time itself, that behaves like a uniform energy density filling the vacuum. This term can act like a pressure with the opposite sign, not a compressive weight, a kind of negative tension, pulling space-time outward as it expands. Under lambda, the acceleration does not require a new substance drifting through the cosmos. It requires only that empty space is not empty in the deepest sense, that the vacuum carries a small, constant energy that never dilutes. Matter thins as the universe grows, radiation thins even faster. But lambda remains patient and undefeated until it dominates by endurance alone. The elegance of lambda is not merely mathematical. It is narrative. It turns cosmic acceleration into a property of reality's baseline, the ground note beneath all fields, all particles, all stars. It suggests that the hidden side is not an event, not a phase, not a temporary deviation, but an eternal characteristic of spacetime. Yet that very elegance sharpens the pain of ignorance, because it offers no mechanism for why the value is so small. Why the vacuum energy that appears in cosmology is not the vacuum energy that naive quantum calculations would predict. A cosmological constant fits much of the data with remarkable calm, but it fits like a mask. Perfect shape. Unknown face. The second door opens into motion rather than constancy. Quintessence. The family of ideas in which dark energy is not a fixed number, but a dynamic field. Often modeled as a scalar field evolving slowly across cosmic time, in such pictures, the universe is not governed by a single immutable vacuum term. It is influenced by a field that can roll along a potential landscape, changing its effective pressure and energy density as the cosmos expands. Quintessence can behave almost like a cosmological constant for long periods, so close to lambda that it is difficult to distinguish. Observationally yet, it carries the possibility of evolution. It can weaken. It can strengthen. It can thaw from a frozen state, or it can track the dominant component of the universe until it eventually takes over. There is a philosophical seduction in quintessence. It makes the why now discomfort feel less like coincidence and more like dynamics. If the field's behavior is tied to the expansion rate, or to the content of the universe, then the era in which dark energy becomes dominant might arise naturally. Not as a cosmic accident, but as a consequence of the field's slow dance with time. The hidden side becomes less like an engraved constant, and more like a tide subtle, ancient, gradual, yet capable of reshaping the shoreline of reality. But quintessence also opens a deeper question. What is the field? And why does it exist? Scalar fields are not foreign to physics modern particle theory already carries. Fields like the Higgs butt, a cosmic scalar field that remains light, stable and influential on the largest scales, demands careful theoretical protection. It risks being disturbed by quantum corrections. It risks coupling to ordinary matter in ways that would have been detected. It invites screening mechanisms, hidden symmetries, delicate constructions that keep the field quiet where it must be quiet and strong where it must be strong. Quintessence offers a living dark energy, but it also offers a universe with more hidden architecture than previously imagined. An unseen machinery operating beneath cosmological measurements. The third door is opened with caution, because it leads to a kind of future that feels like cosmic horror written in equations. Phantom energy. In these models, the equation of state parameter dips below -1, implying an even more negative pressure than the cosmological constant. The consequence is not merely acceleration, but runaway acceleration. The energy density of dark energy increases as the universe expands. Turning expansion into a feedback loop, space grows. Dark energy grows with it, and the growth drives space to expand even faster. Phantom energy is often described as terrifying elegance because it is simple to express and brutal to contemplate. It can lead to a finite time singularity in the scale factor, a scenario known as the Big Rip, where the expansion rate becomes so extreme that gravitationally bound structures cannot survive. First, clusters unbind. Then galaxies loosen. Then planetary systems unravel. Then, in the final approach, even molecules and atoms are imagined to fail as the accelerating expansion overwhelms the forces that hold matter together. It is an ending that does not arrive as a collapse into a final point, but as an unbinding of all points from one another, reality dissolving into separation. And yet, even phantom energy is not merely a narrative scare. It is a theoretically permissible behavior in certain effective field models, though it often comes with instabilities or ghosts that raise concerns about whether such a model can be fundamental. Phantom energy sits at the edge of theoretical acceptability, close enough to be considered, sharp enough to cut. It exists in cosmology's catalog of endings because the data does not yet forbid it absolutely. And because the universe has already proven willing to behave in ways that embarrass intuition. The fourth door changes the framing entirely. It asks whether dark energy is not a thing at all, but a sign that gravity itself has been misunderstood on the largest scales. Modified gravity approaches treat. Cosmic acceleration as a breakdown of general relativity in the infrared, the regime of vast distances and low curvature. Instead of adding a new energy component, these theories alter the rules of how spacetime responds to matter. The acceleration, then, is not driven by a vacuum pressure. It is a property of gravity's long-range behavior. Within this door, there are many corridors. Some models modify the gravitational action, allowing curvature terms beyond the simple Ricci scalar of Einstein's theory, often grouped loosely under FR like families. Others explore extra-dimensional geometries, where the universe is a brane embedded in a higher dimensional space, and gravity leaks or changes character at large scales. Still others invoke massive gravity or scalar tensor frameworks, in which additional degrees of freedom interact with spacetime to produce late-time acceleration. Modified gravity carries a distinctive promise. It links the hidden side to the deepest question in physics. What is gravity? Fundamentally, if general relativity is incomplete, then dark energy is not a substance to be found, but a clue to a missing equation. Yet modified gravity also carries a burden, because general relativity is not weakly confirmed. It is strongly confirmed across many scales. Any modification must reproduce Einstein's triumphs in the solar system. In binary pulsars, in gravitational wave observations, while deviating just enough on cosmic scales to explain acceleration. This often requires screening mechanisms, ways in which extra-gravitational degrees of freedom hide in hide-and-see environments and reveal themselves only in the vast emptiness between galaxies. The hidden side becomes doubly hidden, not only unseen in telescopes, but concealed by gravity itself, where observation is easiest. The fifth door is neither pure dark energy nor pure modified gravity. It is a conversation in the dark sector, interacting dark energy. In the standard cosmological picture, dark matter and dark energy coexist but do not exchange energy directly, except through gravity. Interacting models explore the possibility that the two dominant invisible components are not strangers, but partners exchanging energy and momentum over cosmic time. Such an interaction could alter the expansion history and the growth of structure simultaneously, potentially easing tensions between datasets. It could make dark energy appear to evolve, even if its underlying nature is simple, because interaction can mimic evolution when inferred through geometry alone. In interacting scenarios, the cosmic web becomes more than a gravitational sculpture. It becomes evidence of a hidden economy. Dark matter's clumping, dark energy's smoothness, the rate at which structures form. These become signs of whether the universe's invisible majority is trading energy in ways that ordinary matter never witnesses. Interactions might be weak enough to escape detection in particle experiments, yet strong enough to matter cosmologically. The challenge is that such models can be crafted to fit many observations, and so the burden shifts to predictive fingerprints, distinctive patterns in structure growth, changes in the relationship between lensing and clustering, subtle modifications to how cosmic distances relate to redshift. This door feels plausible because it is modest an interaction term rather than a new cosmic substance. But it also feels unsettling because it suggests that most of reality's energy budget is engaged in dynamics that have never been directly observed. The sixth door opens only when the other doors begin to feel insufficient. It leads into the philosophical extensions of real theory, inflationary echoes, multiverse landscapes, and anthropic selection. These ideas are not introduced as replacements for data, but as frameworks that attempt to explain why constants appear tuned, why vacuum energy is small, why the universe allows complex structures at all. Inflation. The early universe phase of rapid expansion proposed to explain the large-scale uniformity of the cosmos and the origin of primordial fluctuations. introduces a natural arena for vacuum-like energies and scalar fields. If inflation was driven by a field rolling down a potential, it suggests that scalar fields can shape cosmic geometry profoundly. In some extended pictures, the early universe landscape of fields includes multiple metastable vacuum valleys of different energy levels. If a vast landscape exists, then different regions of a larger multiverse could settle into different vacuum states with different effective cosmological constants. In such a context, the smallness of dark energy might not be a single miraculous cancellation. It might be a selection effect. Regions with vacuum energy too large might expand too quickly for galaxies to form, leaving no observers to notice. Regions with sufficiently small vacuum energy would allow structure, stars, and eventually eyes. This line of thought is often unsettling not because it is unscientific, but because it changes what explanation means. It replaces a mechanistic reason with a conditional one. It suggests that the universe's hidden side may be small, not because its symmetry demands it, but because only small values permit the existence of beings capable of measuring it. It is a door that opens onto the limits of inference, where physics meets the philosophy of observation. In this realm, Stephen Hawking's legacy enters in a subtle way, not as a single answer, but as a perspective on horizons, information, and the boundaries of knowledge. Black hole thermodynamics revealed that horizons are not merely geometric features. They carry entropy and temperature, linking gravity to quantum theory. Event horizons are not just limits on travel. They are limits on information. In an accelerating universe, horizons also exist, cosmic horizons that limit what can ever be observed. The hidden side of the cosmos therefore becomes tied not only to the fate of matter, but to the fate of knowledge itself. A universe dominated by a cosmological constant resembles a SpaceTime with a horizon. And horizons invite the same unsettling questions that black holes raised. What happens to information? What can be known? And what is the meaning of physics in a world where observation is permanently limited? Einstein stands in the background of every door because the acceleration is, at its core, a geometric statement. Something is happening to space-time. Whether it is a constant vacuum energy, a rolling field, a modification of gravity, or a hidden interaction, the result is written into the cosmic metric akin to the relationship between distance and time. Hawking stands in the same background because acceleration implies horizons, and horizons imply that the universe is not only expanding, but enclosing knowledge within boundaries no technology can break. Each theory, then, is not merely a model. It is a different answer to the same ending. The cosmological constant suggests a future of quiet domination by vacuum cold. Exponential stretching in which islands of matter become isolated and the cosmic record fades from view. Quintessence suggests a future that can change acceleration might soften, sharpen, or pivot depending on the field's path. Phantom energy suggests a future where the hidden side grows ravenous, unbinding structure until space-time itself cannot hold shape. Modified gravity suggests a future where the rules of attraction and geometry are not what they seemed. And acceleration is a symptom of a deeper gravitational law. Interacting dark sector models suggest a future shaped by unseen exchanges, where the cosmos' invisible majority negotiates its own evolution. Multiverse and anthropic ideas suggest a future in which the very value of dark energy is a selection one valley among many, chosen not by intention but by the conditional logic of existence. Value of dark energy is a selection one valley among many, chosen not by intention but by the conditional logic of existence. In the end, the theories do not merely compete. They circle the same question from different angles, like telescopes aimed at an object too dim to image directly. Each one is a way of translating the silent acceleration into meaning, and the meaning remains suspended in a single spine of suspense. The hidden side of the cosmos is not only driving the universe outward, is choosing what the universe becomes, whether it is an unchanging constant, a living field, a revised gravity, a dark interaction, or a consequence of a wider landscape. It is the same unseen pressure shaping the final structure of time. The story continues because none of these doors, has been conclusively opened. The universe has allowed several to remain plausible, as if it is testing how far certainty can be stretched before it breaks. The hidden side remains invisible, but it leaves fingerprints everywhere on the geometry of distance, on the growth of structure, on the boundaries of the observable sky, and somewhere in those fingerprints lies the answer, not only to what dark energy is, but to what kind of ending the cosmos is preparing to write. Scientific tools and ongoing testing in the present tense of cosmology. The hidden side of the cosmos is not hunted like an object. It is interrogated like a behavior. It leaves no photograph, no spectrum of its own, no particle track that can be held up to the light. It only shows itself through the geometry of distance and the slow choreography of time, through how quickly the universe expands, and how reluctantly matter gathers into structure beneath that expansion. To study such a force, humanity builds instruments that do not see dark energy. They measure what dark energy does, across mountaintops and deserts, in orbit and in clean rooms. The tools are taking shape like a coordinated sensory system, separate eyes that cannot share a retina, can share a conclusion. One maps the expansion history like a fossil record written in redshift. Another measures the soft distortions of weak lensing, turning blurred galaxy shapes into a cartography of invisible mass. Another watches the sky repeatedly, capturing transient explosions and the slow breathing of variable stars, building a movie where the universe cannot hide its changes between frames. And another soon to fly will combine wide-field precision with spaceborne stability, designed to stitch distance and structure into a single coherent test at the center of this present day. Laboratory stands DESI, the dark energy spectroscopic instrument built for a task that sounds simple and is, in practice, colossal. Measure the universe's expansion. History with enough precision that a constant force and an evolving one can be told apart. DESI approaches the problem through spectroscopy, the quiet arithmetic of wavelengths. A galaxy's light is stretched by cosmic expansion, its spectral lines displaced toward the red. That shift becomes a distance proxy, and when distances are gathered by the millions, a three-dimensional map emerges, a distribution of galaxies and quasars not as points in a flat sky, but as structures embedded in time. In March 2025, DESI results were described by the collaboration as tracking dark energy's influence over roughly the past 11 billion years using the largest 3D map of the universe ever made, strengthening hints that dark energy, often modeled as a cosmological constant, might be evolving in unexpected ways. Berkeley Lab News +1, in the language of the hidden side, DESI is an engine of expansion history. It measures baryon acoustic oscillations as a standard ruler, a frozen ripple from the early universe that still lives as a statistical pattern in how galaxies cluster. That ruler does not shine, it echoes. Each measurement adds another rung to a ladder built not of metal, but of correlations. The goal is not merely to confirm acceleration has already been heard in supernova and reinforced by multiple probes. The goal is finer, to see whether the acceleration follows the exact, unchanging cadence of a cosmological constant, or whether it drifts ever so slightly, like a heartbeat that cannot stay perfectly still. Berkeley Lab News +1, this is where cosmology becomes almost forensic. A constant lambda predicts a particular relationship between distance and redshift across cosmic time. An evolving dark energy, whether a rolling field or an interacting sector, would subtly bend that relationship. DESI's strength is not only in the number of objects mapped, but in the era spanned, a long baseline that can catch slow evolution if it exists, or constrain it into near-nothingness if it does not. The hidden side is forced into a corner not by a single measurement, but by the accumulated weight of a map so large that chance fluctuations begin to look like patterns or vanish under their own inconsistency. Berkeley Lab News +1, yet expansion. History alone is only one half of the confession. Dark energy can mimic itself in geometry while betraying itself in growth. A universe can be made to expand in nearly the same way under different theories, but the growth of structure, the formation of the cosmic web, often responds differently depending on whether acceleration comes from a fluid with negative pressure or from a change in the laws of gravity. This is why a second pillar is needed, a tool that measures not only how far things are, but how mass is arranged between them, and how that arrangement changes as time moves forward. Euclid was built for that second pillar, launched to survey the large-scale structure of the universe. Euclid's promise is not a single image, but a statistical universe. Billions of shapes, faint and distant, measured with enough stability to extract the subtle signature of weak gravitational lensing. In March 2025, the European Space Agency released the mission's first batch of survey data, described as a glimpse of Euclid's deep fields and the large-scale organization of galaxies in the cosmic web, an early opening of what is intended to become a deep, long-duration probe of dark matter and dark energy. European Space Agency plus 1 week lensing is one of cosmology's quiet miracles. Light from distant galaxies travels through a universe filled with matter both visible and dark. Along the way, gravity bends space-time and slightly distorts the galaxy's apparent shapes. No single galaxy can reveal the lensing field. Each is too messy, too individual, too shaped by its own astrophysical history. But across millions, the random orientations average out, leaving behind a coherent shear pattern, a ghostly fingerprint of mass distribution. Euclid turns that fingerprint into a measurement of how structure grows, and by doing so, it tests whether the hidden side is merely pushing space apart or also altering gravity's ability to assemble cosmic architecture. European Space Agency plus 1 Euclid's power lies in volume and uniformity. A ground-based telescope looks through a restless atmosphere. A space telescope looks through stillness. That stillness is not a poetic detail, it is a systematic advantage. Dark energy studies live or die on percent-level effects. Lensing signals are subtle, and subtle signals demand stable optics, precise calibration, and consistent depth. Euclid's early data release is the beginning of a long tightening, a gradual sharpening of constraints as the survey grows in breadth and as the pipeline learns its own biases. It is a slow conversation between a telescope and the universe, carried out not in dramatic revelations, but in the steady reduction of uncertainty. European Space Agency plus 1 IF-DESI is the engine of expansion history, and Euclid is the lens of structure. Then the Vera C. Rubin Observatory is something else again, time made visible. Acceleration was first inferred through objects that change the rise and fall of supernova light curves, the calibrated brightness of explosive endings. To push that technique to its limits, the sky must be watched repeatedly, with a cadence measured in nights, not decades. The hidden side cannot be interrogated by a single snapshot. It requires a movie. Rubin was built to film the southern sky at scale, again and again. For years, an observatory designed to turn the dynamic universe into a dataset so large it becomes its own kind of landscape. On June 23, 2025, the Rubin Observatory team revealed its first images, marking the opening of its survey era and the beginning of a new kind of time domain, astronomy at unprecedented depth and breadth. Rubin Observatory plus 2, Max Planck Society plus 2. The importance of Rubin to the hidden side lies in its ability to gather countless supernova, to build lensing maps through sheer statistical power, and to trace how galaxies and their clustering evolve across time. It is not only a telescope, it is a clock. Each revisit to the same patch of sky adds information about change, about transient phenomena that would be missed by slower surveys. Supernova cosmology becomes more precise when the sample becomes enormous, and when selection effects can be modeled with greater confidence. Weak lensing becomes stronger when billions of galaxy shapes can be averaged, and when the survey footprint becomes wide enough to map cosmic variance rather than be fooled by it. The goal is not spectacle, though Rubin will produce that in abundance. The goal is to compress uncertainty until the hidden side has fewer places to hide. Rubin's first imagery reveal was more than a ceremonial moment. It was the first note in a long composition. A decade-long survey is a strange instrument. It does not deliver its main science in 1 year or 2, but in the accumulation of consistency. Its value is the stability of repeated measurement. It's a disciplined revisiting of the same sky until noise begins to surrender patterns. In the context of dark energy, Rubin is a pressure applied slowly, steadily, until the universe is forced to reveal whether its acceleration is the work of a constant, or the symptom of an evolving field, or something stranger still. Rubin Observatory +1, and then, beyond the horizon of the present, waits the near-future heavyweight, NASA's Nancy Grace. Roman Space Telescope. Roman is designed as a wide-field space observatory with a specific cosmological purpose: to measure dark energy with the combined leverage of supernova distances, weak lensing shapes, and the growth of large-scale structure, all from above the atmosphere's distortions. In December 2025, NASA's Jet Propulsion Laboratory reported that Roman was fully assembled following integration of its major segments on November 25th at Goddard, and stated that the mission is slated to launch by May 2027. With the team on track for launch as early as fall 2026, NASA Jet Propulsion Laboratory JPL. Roman's significance is not merely that it will take beautiful images, though it will. Its significance is in the geometry of its survey, a wide field of view, stable imaging, and a mission architecture designed for precision cosmology. The hidden side of the cosmos is a percent-level phenomenon embedded in billions of years of history. Roman is built to treat that subtlety not as a nuisance, but as a target. A large, controlled sample of type Ia supernova can sharpen the distance redshift relation and test whether acceleration has changed its tempo. Weak lensing from space can reduce systematic errors and strengthen constraints on structure growth. Combined with other surveys, Roman can help test whether the same dark energy behavior explains both geometry and growth, or whether the two tell slightly different stories, hinting at modified gravity or an interacting dark sector. NASA Jet Propulsion Laboratory JPL. There is a deeper reason Roman matters to this story, and it is almost philosophical. The hidden side can only be known by consistency. A cosmic constant, a dynamic field, and a modified gravity theory can all be made to fit some subset of the data. What breaks the degeneracy is not a single best measurement, but the agreement between independent methods that should not agree unless the underlying model is correct. Roman is designed to contribute precisely that kind of cross-checking power: multiple probes, shared systematics, unified calibration. A coherent test of whether the hidden side is one thing wearing many masks, or many things acting as one. In this present tense, cosmology begins to resemble a courtroom where the universe is a silent witness. Evidence comes not as testimony but as patterns. Each instrument brings a different form of pattern. Desi brings the fossil ruler embedded in clustering. Euclid brings the shear field written into galaxy shapes. Rubin brings time's cadence and the vast harvest of transients. Roman brings spaceborne stability and wide-field precision designed for synthesis. NASA Jet Propulsion Laboratory JPL +3, Berkeley Lab News +3, European Space Agency +3 together. They are not merely answering the question, is there dark energy? That question is already too small. The real measurement now is the shape of the hidden side across time, whether its equation of state remains locked at a constant value or drifts, whether its influence on geometry matches its influence on growth, whether the data can remain comfortably inside CDM as the error bars tighten, or whether small tensions harden into an unmistakable signature of new physics. Desi's 2025 results were explicitly framed as hints rather than conclusions, yet even hints matter, because they suggest that the next generation of tools will not merely refine a number, but decide whether the number itself is a living function. Berkeley Lab News +1. This is what ongoing testing means in a universe that hides its dominant component. It means building instruments that do not seek a glow, but a deviation. It means turning the sky into a dataset large enough to withstand skepticism. It means treating every possible systematic bias as a rival hypothesis and trying to defeat it with redundancy. It means waiting because cosmic truths often move slower than human impatience, and it means accepting a strange possibility, that the most important force shaping the fate of the universe might never be seen directly, only inferred through the curvature of space-time and the slow procession of galaxies away from one another. In that sense, these tools are not merely telescopes and spectrographs. They are extensions of human philosophy made from glass and silicon, attempts to measure the invisible with discipline, to extract meaning from geometry, and to decide whether the hidden side is a constant written into the vacuum, a field evolving across cosmic ages, or a sign that gravity's rules are not complete on the largest scales. The laboratory is already running. The data is already arriving. The universe is already accelerating. What remains is to learn whether that acceleration is a steady sentence in spacetime's grammar, or the beginning of a change in the language of reality itself. In the end, the universe does not deliver its final truths with thunder. It delivers them the way it delivers everything else, in light that has traveled too far, in signals that arrive too late, in quiet measurements that only become meaningful when the mind learns to listen. The cosmos is a story. The universe tells itself in photons. Every night sky is an archive of ancient messages. A star is not merely seen, it is remembered. A galaxy is not merely distant, it is delayed. The farther the light travels, the older the truth it carries. Telescopes do not look outward into space so much as they look backward into time, catching the glow of epochs that ended long before Earth had a name. There were eras when galaxies were closer, when the universe's expansion was slower, when gravity still held the upper hand with enough confidence to stitch matter into bright structures and long-lived webs. Those eras have not vanished. They still exist as light. The cosmic microwave background, faint, cold, omnipresent, is the earliest page most humans will ever read. It is the universe's first photograph, taken when the cosmos cooled enough to let light move freely. The patterns in that ancient glow are not decorations. They are a blueprint. They are the initial conditions of everything, the tiny overdensities that later grew into galaxies, the statistical seeds of cosmic structure, the first hints that the universe was not perfectly smooth. And then, much later, there were supernova brief eruptions that became mile markers in the darkness, allowing astronomers to measure distance and expansion as if measuring the universe's breadth. There were the fossil ripples of baryon acoustic oscillations, a remnant of primordial sound frozen into the large-scale distribution of galaxies, a standard ruler embedded in the cosmic web. There were the subtle shears of weak gravitational lensing, the bending of light by invisible mass, mapping the scaffolding of dark matter across its immense volumes. Each measurement was a paragraph in a story written without words, and then the story bent into its strangest sentence. The expansion is accelerating. The meaning of that sentence is not only cosmic, it is human. Because acceleration does not only describe what the universe is doing, it describes what the universe is taking away. It acts like an unseen editor working patiently through the cosmic manuscript, removing pages not with fire but with distance. Every year that expansion accelerates, more regions of the universe are pushed toward a boundary of visibility. Beyond that boundary, their future light will never arrive, not because the light is weak, but because space itself is stretching faster than the signal can cross. The consequence is subtle, but immense: the observable. Universe is not guaranteed to remain observable. Horizon is not just a word for where the sea meets the sky. In cosmology, a horizon is a limit on causality and information. In an accelerating universe, horizons emerge as a geometric fact. There are distances beyond which events cannot influence the observer, not because travel is impossible in principle, but because spacetime expands in a way that permanently separates regions from one another. In such a cosmos, no rocket, no probe, no future technology can overcome the boundary. Not because of fuel constraints, not because of engineering, because the boundary is woven into the structure of space-time itself. Acceleration means that the universe is actively reducing what can be known. If the hidden side is constant, if dark energy is a cosmological constant, this editing continues forever. Galaxies drift away until only a local group remains gravitationally bound. Distant structures fade into redshift. Their photons stretch to longer and longer wavelengths, until they melt into the background. The cosmic microwave background continues to cool and stretch until it becomes nearly undetectable. The universe does not end with a final blast. It ends, in a practical sense, with a gradual loss of context. A future civilization might look into the night and see fewer clues. It might live in a cosmos where the evidence for the Big Bang is no longer accessible, where the sky resembles an empty vault rather than an archive in that far future. The greatest scientific truths might become unreachable not because they are untrue, but because the universe has moved them beyond the horizon of observation, and it is in that idea that the mystery becomes philosophical. Because knowledge is not only about what exists, it is about what can be retrieved. In a cosmos where the record is being stretched away, the act of understanding becomes a race against expansion. This is where the humility of modern physics becomes unavoidable. Einstein's relativity reshaped reality into geometry, turning gravity into curvature and time into something that can stretch and flow. It allowed science to predict expansion before it was observed, to describe the universe not as a static container but as an evolving space-time. Yet Einstein's equations also contain the seed of the current mystery, the possibility of a cosmological constant, a vacuum energy, an intrinsic pressure belonging to space itself. And Stephen Hawking's work, especially on black holes, added an even deeper lesson. Horizons are not merely boundaries in space. They are boundaries of information. A black hole horizon hides what falls beyond it. It forces physics to confront what it means to know something in a universe where some regions are permanently inaccessible. Hawking showed that horizons can have temperature and entropy, that the act of hiding information changes thermodynamics, that gravity and quantum theory cannot be cleanly separated where horizons appear in an accelerating universe. Cosmic horizons exist as well. There are regions from which light will never reach. There are distances that will always remain beyond contact. The hidden side of the cosmos therefore becomes a cousin to the black hole mystery, a question not only of what exists, but of what can be known and for how long. And still, despite Einstein and Hawking, despite telescopes and spectrographs and years of observation, the hidden side may never be seen directly. It may remain like gravity itself, known by what it does, not what it is. Gravity was once an invisible force that could only be inferred from motion. The apple fell. The planet orbited. The curvature of space-time was not something the eye could see, yet it shaped everything. Dark energy is similar in its elusiveness, but deeper in its silence. It does not gather into structures. It does not emit light. It does not leave a straightforward signal. It announces itself only through the universe's global behavior, through the stretching of space and the suppression of structured growth. The hidden side is an influence without an image, and it may remain that way. This is why the closing of this story cannot be a neat conclusion. It must be a fork. If dark energy is constant, then the future is not a bang. It is a fading. Time continues, but the cosmos becomes colder, thinner, more isolated. Stars burn out. Entropy rises. Structures decay. The universe becomes a wide, silent geometry, in which distance grows and meaning becomes harder to anchor. Not because meaning is impossible, but because connection becomes rare. A constant vacuum energy suggests a universe that does not collapse and does not explode, but stretches into a long loneliness, where the night sky simplifies until it is almost empty. In such a future, the hidden side is not a predator. It is an inevitability, but if dark energy evolves, if the acceleration is driven by a dynamic field, or by a hidden interaction, or by a modification of gravity, then the future becomes stranger. Reality itself may be temporary. The laws of physics, so stable across human history, may be local agreements rather than eternal commandments. A dynamic dark energy field could weaken, soften acceleration, even allow a different late-time behavior, or it could strengthen, pushing toward more dramatic endgames. It could drift in ways that force physics to rewrite its most fundamental assumptions about vacuum fields and the relationship between geometry and matter, and if the vacuum is metastable, If the universe is living in a long-lived false minimum, then reality might be more fragile than it appears. Not fragile in the sense of imminent collapse, but fragile in the sense that the current rules might not be the deepest rules. The universe might be balanced on a deeper landscape of possible laws, existing in a long pause that could, in principle, end in a transition to a different state. In that possibility, the hidden side becomes not merely the driver of expansion, but a clue that spacetime itself is not finished. Yet even here, the story resists certainty. Because the universe does not give its secrets freely, it allows multiple explanations to remain plausible at once, as if it is testing the limits of what can be inferred from geometry and light. The measurements tighten, the instruments sharpen, the maps grow larger. But the hidden side remains behind a curtain, visible only as a silhouette drawn by cosmic evolution. And perhaps that is the deepest lesson. The cosmos may never become fully transparent. It may always keep a portion of itself in shadow, not out of malice, but because the universe is larger than any observer inside it can fully grasp in the present era. Humanity lives at a strange intersection of capability and timing. The night sky still contains distant galaxies. The cosmic microwave background is still measurable. Supernovae still appear as calibratable beacons. The cosmic web still leaves its imprint in lensing and clustering. The archive has not yet been stretched beyond reach, but acceleration is working. Quietly, the hidden side is editing slowly, and the final question is not only scientific, it is existential. It's meant to linger after the screen goes black in the last. Music dissolves into silence. Is humanity measuring the universe's acceleration? Or watching the moment the cosmos begins to leave itself behind?